Well, thank you very much, of course, to the organizers and for the very kind introduction, which I have to tell you, I'm not sure my mother could have done any better. But anyway, there are a couple of things that I need to tell you right up front. First of all, the discussion that we're about to have is not going to be like your father's Oldsmobile type of discussion. You'll see what I mean very shortly. But we're going to talk about things that are very important, and especially to you. And because of the time, which I get is 28 minutes. What? I mean, not 25, not 30. I've given a lot of talks in my time. 28 minutes? Who does that? 28 minutes is what the clock says. All right. But anyway, let's start with the punchline to make sure that you get it, because it's very important that we together, and I'm not kidding when I say we have to save the planet, your planet, because you will inherit all the problems that we're going to talk about. You are going to see how chemistry, and in particular organic chemistry of carbon, every one of you, chemistry is all over the place. It is in you. It is you. Well, all right. For this talk, right, every one of you means only human beings. If you happen to be an alien, tune out. This is not for you. But for the rest of us, we are involved here. And chemistry, organic chemistry in particular, is everything. Everything. The clothes you're wearing, the materials, the rug I'm on is chemistry, right? And so the question I'm going to ask you right here is, at the end, and you now are going to be a lot smarter, are you in? Because we need your contributions. You will inherit the mess that we have made today. So I'm not here to convince you about the Earth and how it's been around for 4.5 billion years. And I'm not here to argue with you about how human beings, shown right here, there's some evidence that maybe it's 300,000 years. I'm not going to debate religious this or that's not the point. The point is that if you consider one or the other, right, no matter how you look at this timeline, these numbers relative to modern organic chemistry add up to nothing. It doesn't matter. But modern organic chemistry, which is only 200 years old, 250 years old, is done in petroleum-derived materials. We are a petroleum-based society. Organic chemistry gets done in organic solvents. Why? Think about nature. 4.5 billion years, and that oil is in the ground. And how much did nature, during the entire period of the Earth's existence, use of that oil? It's kind of a joke, because the answer is 0. How come we, over 250 years, is using it up at an alarming rate? You're going to need it. And the industries that I'm going to focus on, fine chemical industry in particular, includes, for example, the pharmaceutical industry. I think that's kind of important because they make the drugs that keep people alive. I'm going to tell you about the fine chemical industry from the agricultural standpoint. They make the herbicides, the pesticides that feed the planet. I think those are pretty good. There are more. It just doesn't matter what those are. But you get the idea. Why are all these things made in petroleum base that we are consuming at an alarming rate when we don't have to? Because nature, for 4.5 billion years, did chemistry. How did nature do all this chemistry? How is it done in us? We're mostly water. Think about the planet. 70% is water. What do we send to galaxies and planets and everything? What do we look for as a sign of life? Water. So what happened here? How come we're consuming our petroleum, which you're going to pay for? Because it's going to be out. Can you imagine that? That you need health care and you go to the doctor's office and you know that there was, or there is, hopefully some kind of treatment for this disease for your children, your parents, whatever. And somebody says, well, we used to be able to make that. We can't make that anymore because we don't have the catalyst, or we don't have. Are you going to be happy about it? Of course not. The day is coming. So we have, on the one hand, nature at 4.5 billion years, and we have modern organic chemistry at 250 years. Who are you going to take? Which one are you going to bet on? I'm not an idiot. I'm going with nature. How did nature figure it out in us? We're proof that chemistry and water, we're 70%, what 50%, 60%, whatever. What about all the molecules that are not soluble in water? That's the claim by modern organic chemists. We can't use water because nothing organic is soluble in water. Isn't that right? Yeah, it's not a solvent. But nature figured it out. Nature has all the answers. So, for example, nature has in us put bile acids. This is just representative sampling. And what happens is these acids, sulfonic acid, have a proton. The proton comes off. It makes a salt. And what happens to these bile acids? The answer is, where are all these water-insoluble compounds? They're in micelles. And so they look like this, where 50 to 100 of these molecules come together, and they form these micelles. So on the inside would be, let's say, whatever it is we're trying to solubilize, which is insoluble in water, but this is the greasy interior, and on the outside are all those salts interacting with water. Nature figured all this out. So what do we have for CoQ10? Every one of us has it. If you don't have it, you can't breathe. You don't get energy. Totally water insoluble. You've heard of vitamin E. What about the polypeptides? What do we do with all these molecules that are insoluble in water? Nature figured it out billions of years ago. And yet, all these important industries, and there are more than I've named, flavors and fragrances and all these sorts of things, they make these compounds in organic solvents, and then what happens to them? Where do they go? They get burned. And that's a problem, right? We're going to talk about that in a moment. But if this is the answer, and you take these materials, these so-called micelles, because we have other things, we have membranes, we have vesicles. Nature puts these water-insoluble molecules in these various places. So let's just talk about micelles. And they're small, 10 to 15 nanometers. That's, let's say, roughly 100 angstroms. They're small. We can't see them. Which means that if you put them into water, like a glass of water, it looks like water. And oh, by the way, that's the correct pronunciation. Water. I'm from New York. I know how to talk. I don't have an accent. You have the accent, okay? I'm telling you now, right? It's water. And that's what it looks like because they're too small. So we figured, how can we take this 4 billion-year-old concept and modernize it so that we could do modern organic chemistry in water? And the idea came up, let's take what we saw on the previous slide, and now with a vitamin E base, let's pegylate it. So this would be the species on the outside of 50 to 100 of these that come together, and now the vitamin E would be on the inside, and that's where things would go. And if you happen to worry about the downstream processing of a polyethylene glycol, which some companies do, we came up with a more recent version called SAVI, which is a polypeptide known to be biodegradable. So there's no problem with these materials. No one is going to come. If you're a process chemist making a drug and you use this chemistry, 3 o'clock in the morning, you have to stop a reaction and you're tired. And you pull the wrong lever, everything gets flushed down the drain. I can assure you, no one from the EPA or the FDA, if it still exists today, is going to come and say, excuse me, you're putting too much vitamin E in the environment. That ain't going to happen. So they're safe. And the fact of the matter is, and I do not recommend this, I'm going to say this 2 or 3 times, I do not recommend this, is that if you run these reactions in water where the inside is just derived from vitamin E, you get everything out, drink it. Yeah, you could drink your reaction mixture. And you know what would happen? You'd be getting vitamin E. Bonus. Again, don't do it. Don't do it. But they're safe. So can we modernize this chemistry? Because we have to. We don't want to use the organic solvents, because what happens to anything organic when it's burned? It generates CO2. Does that start to ring a bell? Greenhouse gas? Climate change? We're going to talk about that right here. This, again, is not me. This is the American Chemical Society Green Chemistry Institute telling us that the gorilla in the room is organic solvents. And if you take that number, 56%, and add to that the water that you need to work up reactions when they're run in organic solvent, the sum total of that, it's not higher math, is 88%. This is what we have to get rid of. Because these organic solvents contain carbon, they get burned. So I'm going to say the quiet part out loud. This is the part that makes me, well, I have no friends, right? Because what I'm about to tell you is, when you burn these organic solvents and you generate CO2, are we contributing, the entire organic community, worldwide? And I'm just talking about the fine chemical industry, but this is all of chemistry. Are we contributing because we're using petroleum-based organic solvents to climate change? We are. So this is your world. I don't have to tell you about what happens in Texas. I don't have to tell you about New Jersey. New Jersey is underwater, right? We see all the things that are happening. We all understand that. But we, as organic chemists, are contributing to that because we don't pay attention to those 4.5 billion years that nature showed us as we're proof chemistry in water is the way to go. So, okay, that's the first part, organic solvents. Now, let's talk a little bit about energy. In order to get A plus B to equal C, we have to, most of the time, we have to heat. Sometimes we cool, but most of the time we have to get that activation energy so that things will react. Unfortunately, we haven't solved the 100% yield problem. So while we provide the energy needed for A plus B to go to C, we also get byproducts. Well, if you get byproducts and you have to purify, especially if you're eventually going to submit this to the FDA as a package, you got to know what every impurity is. You want reactions to be clean. And what happens when you get impurities, byproducts? More time, more energy, more waste is created, more contribution to climate change. And then we have the endangered elements. Again, this is not me. This is all well known. And look at the transition metals. They're all endangered. The king of transition metal chemistry, as you will see in a moment, is palladium. Palladium catalysis is king. It's endangered, for sure, because we're using too much of it, and the estimate is in 100 years, it's gone. Just gone. So that's why I say, imagine going to the doctor and that drug, sorry, we used to be able to treat it, we can't treat it now. You're not going to be happy about that. That day is coming. So let's very quickly, because I'm running out of time already, talk about how, in palladium catalysis being king, we can contribute by taking advantage of what, well, let's just say nature has provided us. And when we do this chemistry, nature, in its glory, doesn't pat me on the back, doesn't pat the students on the back. What nature says is, what the hell took you so long to do this? It's been available for a long time. So let's take a look at Nobel Prize winning chemistry in 2010 using palladium catalysis by Suzuki, Negishi and Heck. which is used every day, and compare. And what I'm about to show you is that if you go green, if you do it environmentally responsibly, you will always win 100%. And you will see, I will point out, faster, better, cheaper. Why would companies not want to make more money? I don't understand it. Because when they do, they're green. And why wouldn't they go green? Because they're going to make more money as a bonus. I don't understand it either. But here, let's take Suzuki couplings to start. It's only one slide per name, per reaction. You're going to get it, right? So the bottom line is lots of catalysts were created. We know the new rules for doing the chemistry under these micellar conditions in water, and we don't need a lot of palladium to do it. So if, according to others, there's 100 years left, if we can just do the chemistry with 10 times less palladium, then that 100 years becomes 1,000 years. Problem solved. So these catalysts, and you can see them up here versus ours. And again, we want to make in a Suzuki coupling that bond to make a biaryl. And here are the numbers. Guess what? We win. Not to mention the economics, right, of using 1,500 ppm. That's 0.15, 10 times less than everybody else. And here's an example, again, another example. We win again in terms of yield, etc. 500, 0.05, 100 times less than everybody else. It's doable. It's known. There it is. And these are just examples picked out of the publications. Now, Negishi couplings, right? Let's talk about briefly. The best I could do was find sort of equivalents. I couldn't find the exact molecules, but they're pretty close. And you could say, well, the yields, come on, they're roughly comparable in yields, but we're in water and they're not. And they're using dangerous, yes, carbon-containing solvent. And that's there because you don't want to have to do that. But that's what's in the literature, and you pay the price because of its contribution to climate change. So Heck couplings, once again, notice we're in water. Look at the numbers, right? For the same molecules, we win. Now, you could argue, you have to use a little bit of organic solvent there. Yeah, because everything is different. Some substrates are not particularly soluble. They're called what's oftentimes called brick dust. Sometimes you need a little bit of a solvent, which is water miscible, to soften that lattice a little bit, to help it get inside that micelle. And by the way, from the energy standpoint, let me make sure that everybody appreciates the analogy to this chemistry in water, where nothing is soluble on the outside. We're only using 2 weight percent, so 98% is water. We're not in water in the sense of the compound being dissolved in the water. We're inside the micelles. That's where the chemistry is taking place. So if you dump in your A plus B and they're not soluble in water, isn't it kind of obvious? They're all going to want to get inside the micelle. That's where the action is. So the analogy is the following. Imagine that you have to get into the elevator, and that elevator holds 50 people, but you shove 500 people in that elevator, and you're kind of like booked in there because you got a long ride down, depending upon how long the reaction is, 1 hour, 2 hours, 5 hours. You're like this. What does it take energetically for the person next to you to have a problem with that? Because you move an elbow, somebody goes, hey, what are you doing? That hurt. Well, it's the same thing, chemistry and water. Look at the temperatures, right? 40 degrees, 45 degrees, 30 degrees, 25 degrees. That's all room temperature. Let me assure you, that's room temperature if you go to Arizona today, right? So it depends what you define as room temperature, but the temperatures are coming down because you're so 10 times, in fact, more concentrated in that elevator, in that micelle, than everybody else doing chemistry in waste-generating organic solvents. But you can see we win. Okay, Now, here's a case, again, only for human beings. You all went through the pandemic. Some of you may know about this drug, Paxlovid. What does that mean? Well, it's a drug that's on the market. You could take it if you have a mild case of the pandemic. You take it, it cures it in, 3, 4, 5 days. It's put out by Pfizer. The key ingredient is nirmatrelvir, and they only made $18 billion with a B dollars on one drug last year. $18 billion. Now, did they use our chemistry? How do we compete with a company that's making that much money and so many thousands of people all over the world to make this drug? Well, let me tell you, the Gates Foundation, as in Bill and Melinda Gates, came to us and they said, can you make this drug here, nirmatrelvir? Because obviously there's a lot of people in what today is called low-income countries. We used to call it third world. It's not politically correct. Low-income countries where it's all about cost. Can we make it? And it's a polypeptide. You can see blue, red, right? You can see the bonds that need to be made. There are 2 key bonds here. And they said, we want you to make this drug for those people, but we don't want you to use any traditional coupling reagents. Why not? Because the byproducts, which are ureas, times 2 is huge, and we don't have a place for it. So can you do this chemistry without using the traditional chemistry, which, by the way, is used by Pfizer? And I said, got my guys together around the table. I said, guys, can we do this? They go, yeah, we can do this. Okay, so we came up with a new reagent to do that key amide or peptide bond formation, where the byproduct is this sulfur attached to this pyridine ring, this thiopyridine ring, which we isolate, use it again to make the reagent, no waste. So to make a long story short, kind of blew them away. Why would anybody think that a company makes $18 billion on one drug, overall $30, $40 billion a year, with thousands of people could compete with green chemistry and my guys? Impossible. So we blew them away. And then I thought we were done, right? We published the paper, everything looks good. No. Gates Foundation comes back, says, can you do it better? Say, what? Like, we're all on the phone. Like, did I hear that right? Yeah, they want us to do it better. So I got everybody around the table. I said, what are we going to do? Can we do it better? What do you think? What do you think? Yeah. So to make a long story short, we quoted Obama, right? And we did it. And in fact, we did it in one pot. You can't beat that. You just can't beat it. So as we published, we made the drug in one pot. Pfizer told us how they did it. They published lots of papers. And because they cannot compete with going green, they did the only thing in print that they could possibly do. Completely ignored us. Completely. It's not in there, even though it was published back in 2022, and their paper came out in 2020. Didn't matter. They cannot win. So I put out this sort of opinion, view, whatever you want to call it. And the lesson is, it's not about me. It's not about my students. It's about going green. If you listen to nature and you do chemistry under green chemistry conditions, 100%, right? 100%, you will always win. And why is that? I'm going to tell you. Because these are the ingredients in the process chemist spreadsheet. This is what has to be done. Everybody needs cost of goods, the raw materials, yes, their way, green way, etc. But then what about the solvents, the organic solvents that create all kinds of flammability issues and waste generation, climate change? What about all those? You have to buy them, and then you have to pay actually more to get rid of them. Did you see any organic solvents in our chemistry? No, we don't use them. We follow nature's lead. And then what about the reagents? Well, you saw, for example, we develop our own so that we can recycle it. We recycle the water. We recycle everything. And then what about energy? Well, you saw how we come down in energy. It's expensive. Talk to anyone in Europe. They'll tell you. And then in terms of the catalysts, right, the endangered metals, we're 10 times less. The prices of those metals are like in the 70s. Imagine 10 times less. So the bottom line is, these are all gone. Of course we're going to win. We always win because we've gone green. So let me just tell you, yeah, these are the things that we've talked about, right? How you can do all kinds of modern chemistry because you know what, those surfactants, they don't give a damn about what you put in it. They don't recognize this group A or B or C or D. They don't care. So we do all kinds of chemistry the way nature intended it to be in water, right? And as a result of that, we don't touch the petroleum in the ground. You need that for future generations. You need that for heating homes. You need that for things other than chemistry. Doesn't have to be that way. We're proof of that. So, better chemistry if you go green, for sure. And then the last part, which I don't have time to talk about, is because we're doing this in water, aren't enzymes in water? Isn't biocatalysis in water? So all of a sudden, why would we work a reaction up done with chemistry in water to put it back in the water to use an enzyme? That makes no sense. But if you have water as the common denominator, we can pull anything off the shelf. We can pull chemistry reagents. We can pull enzymes, dump it in, keep going. 2, 3, 4, 5, 6 steps consecutively in one pot. We're doing that right now. All this technology is known. So you could wonder, we could talk about this later because I'm running out of time, right? Why this isn't being used. So I'm just going to say thanks because they don't let me in the lab, right? They don't. Get out, right? They're doing the chemistry. All the students at all levels are actually doing this. I want to thank the funding agencies. Obviously, they're paying the bills for all of this. And more instructions which say, we're ready for questions because we got 30 minutes and I got 16, 15, 14 seconds. That's not bad, right? I'm done. Thank you very much.